Friends, in this video, we are detailedly study about the static Scherbius drive for your induction motor. So let's begin. In this video, we want to study the static Scherbius drive. But friends, before we going to start that particular bit, we should know why we want to study the static Scherbius drive. So friends, as we know that there are different speed control methods of your induction motor. So speed control of induction motors are classified as we know that first one, the method which is called as the pole changing method. The second method of your speed control, that will be called as the stator voltage speed control technique. Then after that we can study the speed control method which is called as the variable frequency speed control technique. So in variable frequency speed control technique, we can change the frequency of your induction motor. By means we can get the variable frequency control. After that, we had already discussed the fourth speed control technique, that is called as static rotor resistance speed control technique. Rotor resistance speed control technique. So after that, we have another speed control technique, that the speed control technique that is called as the slip power recovery scheme. So friends, as we know that the first three speed control methods, that is slip power recovery method, that will be that three speed control methods are only applicable for your squirrel cage and slip ring induction motors, that is both. But as we know that the last two speed control methods are only applicable for your slip ring induction motor, or we call it as wound rotor induction motor, that is slip ring induction motor. So friends, as we know that there are a lot of disadvantage of the static rotor resistance speed control technique. That's why we want to rectify these the various disadvantage of the static rotor resistance speed control technique. We are employing the next speed control technique, that is called as slip power recovery scheme. So friends, as we know that in slip power recovery scheme, we are feedback the power which will be wasted in the rotor resistance, that is feedback to your source. So the slip power, now we can feedback to the source. So that's why this is called as a slip power recovery scheme, that we had already discussed in the last video. So friends, as we know that these slip power recovery schemes are again classified as two types, because as we know that the slip power recovery schemes will provide you the speed control that is below the synchronous speed and above the synchronous speed. So the slip power recovery scheme is again classified as, first one is called as static Scherbius drive, that is static Scherbius drive, and second type of the slip power recovery scheme which is called as static Kramer's drive. So friends, in this video we want to study the first slip power recovery method which is called as static Scherbius drive. Basically, this static Scherbius drive is employed for the speed control of your wound rotor induction motor, that is called as the slip ring induction motor, and this static Scherbius drive will provide you the speed control below the synchronous speed, because we have the fundamental concept of the slip power recovery scheme. So in slip power recovery scheme, friends, we are controlling the power, that is PR. If as we know that this will be the fundamental formula, that is PM is equal to PG minus PR. Suppose we are changing the value of this value of PR, that is PR is the power absorbed by the voltage source. So while we are changing the value of your PR, we can control the speed of your induction motor, whether that will be below synchronous speed, whether that should be your above synchronous speed, that will be the depending upon the sign of your PR. So basically in static Scherbius drive, we are speed control that is below synchronous speed, means obviously below synchronous speed. So the value of your PR should be your positive, that we had already discussed. So the speed below synchronous speed. Okay. So the speed control will be possible in static Scherbius drive for your wound rotor induction motor. We call it as the slip ring induction motor, that is below the synchronous speed, because in static Scherbius drive, friends, the value of your PR, that is the value of your PR, that is PR value is positive. If the value of the PR is positive, so obviously the value of your PM will be lesser. If the value of your PM, that is mechanical power, will be lesser, then obviously the speed control will be possible for the below synchronous speed. So that will be the concept of your static Scherbius drive. So friends, we can understand the detailed understanding or the working principle or the driver circuit of your static Scherbius drive. So friends, first of all, this will be the actual circuit diagram of your static Scherbius drive. Friends, basically this will be the modified version of your rotor resistance speed control technique, because as we've seen that in the rotor resistance speed control technique, we are using that particular rotor resistance in circuit, and the most of the power will be wasted. So that's why we can applying the next speed control, that is slip power recovery, means that particular slip power will be recovered through some of the mechanism, and that mechanism is called as the static Scherbius drive. So friends, we can understand what was the concept. So friends, first of all, this will be the three-phase supply, that is RYB, which is given to you. So this will be the part of your stator of your motor. This will be the part which is called as rotor of your motor. This will be your inner part which is called as rotor. So as we know that we are giving the supply to the stator winding and taking the output from your rotor winding. So this will be the stator winding. We are giving the supply to the outer, that is stator winding, and we are taking the supply from inner, that is rotor winding. So in the rotor circuit, we are connecting the resistance through switch, where S1 is called as the switch, okay, where S1 is called as the switch, and we are connecting resistance, okay. So we are connecting three resistance in three phases, that is RYB, we are connecting three phases, where we can write, that is where S1 is called as the switch, that we called it as the starting switch of your induction motor, that is starting switch. Then as shown in figure, there is another switch which is called as S2. So as we know that the S2 switch, which will be the, basically we call it as the operational switch of your static Scherbius drive. So it is operational switch, switch number S2. Then this will be called VD1. Basically this the portion which is called as the VD1. VD1, it is the voltage across the diode bridge rectifier. So it is voltage across, that is diode bridge rectifier, diode bridge rectifier, because as we seen that in that particular diagram we are using diode bridge rectifier. Then ID, basically ELD is the inductance, that will be inductance for the smoothing out the ripples in the circuit. ID is current flowing through the DC link resistor, current flowing through inductor, that is called as ID. And VD2 is called as voltage across the inverter circuit. The VD2 is the voltage across the inverter circuit, okay. And this is the inverter circuit, okay. Basically this will be the inverter circuit. So this will be the first, which is called as rectifier, and this will be called it as the inverter circuit. So from inverter circuit we are connecting one transformer, and which the transformer which will having the terms, that is M. So as we know that we are having one parameter which is called as N. It is the stator to rotor turns ratio, that is stator to rotor turns ratio, because as we know that friends, in the static Scherbius drive we are feedback the energy of your system through that particular supply, okay. So we are feedbacking the waste of the energy which will be previously wasted in the rotor resistance, that is feedback to your source. So friends, this will be the N is the stator to rotor turns ratio, and M, which is called as the supply turn ratio. Basically it is supply turns ratio, means it will be the turns ratio of your transformer, that is called as M, okay. So N and M. So these are the various elements of your circuit, So now we can understand what was the working of that particular circuit. I think everyone has got the clear what are the different element, what are the different parts. So this will be the your induction motor, this will be the your rotor resistance, this will be the switch number 1, switch number 2, this will be the rectifier, this will be the inductor, this will be the current flowing through the inductor, this will be the voltage across your inverter circuit. And as we know that this will be the N is called as the stator to rotor turns ratio, because as you know that this will be the circuit referred to stator to rotor, so this is called as N, stator to rotor turns ratio, and M is the supply turns ratio. As we know that while we are supplying the power, that is rotor resistance power, that is called it as a slip power feedback to the source, so by means of some of the device, that so the device is called as a transformer, and transformer will having its turns ratio which is denoted by M. Okay, so these are the various terms. Now we can understand the detailed working of your slip power recovery scheme. So friends, now we can study the detailed working of your static Scherbius drive. So again we have to understand this is the three phase, that is RYB supply. Okay, so this supply will be given to your stator of your induction motor. This will be your rotor circuit. Okay, so these are the rotor circuit, which is rotor bar. Okay, so these are called as the rotor bar. This will be the rotor circuit. Okay, and we are connecting one resistance, or we are connecting resistance in series with that particular rotor circuit for each and every one phase. So this is for R phase, this is for Y phase, and this is for B phase. So friends, we can understand first of all the operation. So friends, for the operation of your slip ring induction motor, basically this is a slip ring induction motor, because as we know that the slip power recovery scheme or static Scherbius drive we are applying only for your slip ring induction motor. So friends, when the motor will start by giving the supply to the stator winding, then the rotor will be rotate. So in rotor circuit we are connecting we are connecting each and every one phase with the help of variable resistance. This is called as R. So friends, at the starting of your circuit, the condition of your S1 should be closed. Okay, so at the starting of your static Scherbius drive, friends, the condition of your switch S1 will be closed. So if the condition of your S1 will be closed, then the total resistance will be basically inserted in your rotor circuit. So this will be the induction motor, that is slip ring induction motor, will be works as a rotor resistance speed control technique. But friends, when this induction motor will be runs at near about its 80% of its rated speed, then the automatically this switch S1 will be open, and now the switch number S2 will be closed. So friends, first of all understand the working principle. When we are giving the supply to your induction motor, so the rotor circuit will be operated as a rotor resistance speed control technique, means at the starting of your static Scherbius drive, the condition of your S1 will be closed. So when the S1 will be closed, the motor will be running. So if motor will gain its the 80% of the rated speed, at that time the switch S1 is automatically open. So this switch S1 will be automatically open, and now the switch S2 will be closed. So friends, what will happen while we are closing the switch number S2? Then the power which will be available in the rotor circuit, that will be the given to that particular supply of your converter 1. So as we know that the power of your rotor circuit, now it is AC power, because in previous speed control technique, rotor resistance speed control technique, this power will be wasted in the resistance. But in this scheme, slip power recovery scheme, when the motor will reaches its the 80% of your speed, then automatically the resistance are out of the circuit. Okay, then the whole resistance power, now it will be feedback to your first converter. So friends, as we know that this is a diode, that is a uncontrolled rectifier. So as we know that what will be the function of your rectifier, so this rectifier will convert basically the alternating supply into a direct current supply. So this uncontrolled rectifier, so this all power will be feedback to that particular rectifier circuit. So the voltage across this rectifier circuit, this is the three phase rectifier circuit, so the voltage which is called as VD1. So what will be the function of that particular rectifier? This rectifier will convert that the AC supply which is received from your induction motor, that will be converted to the DC supply by means of this uncontrolled diode rectifier bridge. Okay, so this is called as the first converter, which will convert that the alternating supply of your rotor resistance power, that is called a slip power, into a DC supply. So friends, in the circuit we are connecting one inductor that is called as ELD. Okay, what was the function of that particular inductor? So we are getting the DC supply from that particular rectifier circuit. So this DC supply will contain some of the ripples. So to smoothing out this ripple, we are using this inductor circuit, because the inductor will, what will done, it will basically smoothing out the ripples in that particular DC circuit. And the pure DC supply is across a second converter circuit. So the current flowing through that particular inductor, which is called as ID, and the direction of this current showing by this arrow. Okay, so now this will be the part of the second converter. Basically this is the second converter. It is a basically thyristor feed inverter circuit. So as we know that in a three-phase inverter circuit, we are getting the DC, that is a pure DC. So what will be the function of this particular inverter circuit? It will be convert that the DC supply into AC supply, because as we know that the AC supply will be converted by DC by the rectifier, smoothing out the ripples, and we are getting pure DC. So what should be the function of this inverter circuit? It will again convert that DC supply into AC supply. Okay, so by means of that particular inverter circuit. Okay, so friends, we are controlling the power of your rotor resistance by means of this firing angle of your inverter circuit, because as we know that friends, the first converter will be only uncontrolled. In the first converter we are using only diode, but in second converter, that is called as the inverter circuit, we are using the thyristor, and by the changing of the firing angle of your thyristor, we are changing the actual rotor power, which is called as the slip power. And the voltage across this converter circuit will be represented by the VD2, where VD2 is the voltage across your three-phase inverter circuit. So friends, now this inverted power, that is the AC power, will be feedback to your source through one device. That device is called as a transformer. So friends, the AC power which will be getting from the inverter circuit, that will be again feedback to the source by means of one device. That device is called as a transformer. Okay, so as we know that the turns ratio of this transformer will be represented by M. So this M has to 1 ratio. So friends, in this particular Scherbius drive, in previously when in a rotor resistance speed control, that will be energy is wasted in the rotor resistance. By means of in a static Scherbius drive, we are feedbacking or that particular waste of energy, which is called as, we call it as the slip power. We can convert that slip power by means of the rectifier circuit, so that the AC supply will be converted into DC. And now we are changing the firing angle of your inverter circuit. We can change the value of your slip power, and now this slip power is again feedback to your supply. So in this way friends, the slip power recovery scheme will work, and this will be the actual working principle or the detailed working of your static Scherbius drive. Okay, I think everyone has got the clear idea about this. So friends, keep in mind, in concern with your static Scherbius drive, there are two converters are there. First converter, which is called as converter number first. So we are getting the output voltage of that particular converter, which is called as VD1, and a second converter, that is VD2. So for the sake of understanding, now we want to get the basic equations of that particular converter circuit, and we can derive what should be the value of the slip power that will be recovered by this scheme. So friends, now we can rewrite the fundamental equations of your converter circuit. So friends, first of all, we neglecting the stator and rotor drops. So first term is that now we are neglecting the stator and rotor drops, that is the stator and rotor drops. So while we are neglecting the stator and rotor drops, friends, we are getting the output voltage of the converter, that is VD1 is equal to 3 into root 6 by pi into SVN. So this where we can rewrite VD1 is the voltage across your converter 1, that is S is called as sleep. As we know that this will be the sleep is equal to NS minus N upon NS. V is the voltage. Okay, V is the voltage of your supply. N is called as the stator to rotor turn ratio. Stator to rotor turns ratio. So this will be the first equation. Why we multiply 3 into root 6 by pi? Because it is a three-phase diode rectifier. Okay, so this will be the equation number first. Okay, so for your converter number 1, similarly we can rewrite the output equation of your converter number 2, that is VD2, that is 3 into root 6 by pi into V by m into cos phi or cos alpha. We call it as cos alpha. This will be the equation number 2, where we rewrite that is V is equal to the voltage, that is supply voltage, and m we call it as the source side converter, or we call it as the source side converter turns ratio, that is turns ratio of the transformer circuit of transformer. And as we know that alpha is the firing angle of your inverter circuit. It is firing angle of your inverter circuit. So we are getting this two fundamental equation of your converter 1. This is called as converter 1's equation. This will be very important equation, because this will be using for the next calculations, VD1 and VD2. So this will be for your as we know that this is for the rectifier and this is for your inverter. Now friends, we are getting what should be the output slip power. So obviously, because that is, now we can neglecting the drop across the inductor. So we are getting one important equation in concern with that. So what should be that particular equation? So that the equation will be VD1 plus VD2 is equal to 0. What do you mean by VD1? What do you mean by VD2? I can again show you friends, because this will be the very important concept. This will be the VD1. VD1 means what? This voltage will be the across, that is a voltage across your converter number first. And what should be value of VD2? It will be the voltage across your converter number 2. So this will be the converter which is called as the rectifier, and this will be the converter which is called as the inverter. Okay, so we are equating this term when we are getting neglecting drop across the inductor. We are getting the output equation, that is a voltage VD1 plus VD2 is equal to 0. Now we can compute, or we can substitute the value of the VD1 and VD2 into that particular equation. So friends, now we can substitute the value of VD1 and VD2 into that equation. VD1 plus VD2 is equal to 0. So we can get one important term, that is the equation of VD1, that is 3 into root 6 by pi into S into V divided by N plus 3 into root 6 by pi into V by M, that is cos alpha, is equal to 0. Now friends, we are equating this term. So we are getting that is 3 into root 6 by pi into S into V by N is equal to minus. We can convert this term. So we can get minus 3 root 6 by pi V by M cos alpha. So friends, in that particular equation we can cancel out this term, this term, this term, and only terms are remaining Sn, that is m cos alpha. So we are getting one important equation in concern with your sleep. So we are getting the equation that is minus n by m into cos alpha. So we are getting one very important equation in concern with your sleep power, and that the sleep power equation is equal to S is equal to minus n by m, because this m kept as is, this n will be moved towards the right hand side. So S is equal to minus n by m cos alpha. Now friends, for the sake of understanding, we are just getting one important equation, or we can put that the ratio of the stator to rotor turns ratio and the source side transformer turns ratio, we can substitute the n by m is equal to a. Okay, so we are getting one important equation in concern with your sleep, that is S is equal to minus a cos alpha. So what do you mean by the a? So a is called as n by m, and what do you mean by n by m? N is the stator to rotor turn ratio and m is the converter side transformer turns ratio, which is called as the M. Okay, so this will be the fundamental thing. So after that, friends, we check by the changing of this firing angle, we can change the value of your slip, and with the help of that particular stator to rotor turns ratio and the transformer turns ratio, we can control the value of your slip power. So friends, now we can understand what should be the firing angle of your converter circuit. Okay, so for the sake of the firing angle of your converter circuit, so the value of the alpha, because as we know that what do we mean by the alpha, it is the firing angle of your inverter circuit. So the maximum value of the alpha is restricted to basically 165 degree for the safe commutation. So friends, as we know that while we are changing the value of the alpha, so what should be the value of the alpha? It will be restricted to only 165 degree. Why we want to restrict this value of the alpha to the 165 degree? Because as we know that for the commutation failure, because if we are increasing the value above, that is 165 degree, then the commutation problem will be occur, and if the commutation problem will be occur, your circuit will not be work proper. So friends, the value of the alpha is limited to the 165 degree only. So friends, this will be the representation of your torque and speed characteristics with respect to your change in firing angle, which is called as alpha. So in the first thing that we can take, the value of the firing angle will not be greater than 180 degree. So obviously the firing angle of your alpha is obviously greater than 90 degree, because as we know that while we are using the converter circuit, so if it is the converter circuit will be operated below the 90 degree of your firing angle, then it will be work as an rectifier. If you are increasing the value, that is a firing angle of your converter circuit that is greater than the 90 degree, then it will be work as an inverter. So friends, the value of your alpha will be restricted in between 90 degree to the 180 degree. So the maximum value of your alpha should be 165 degree. Why we are taking the value of the alpha should be 165 degree? For the safe commutation, if we are increasing the value of alpha greater than 165 degree, then commutation problem will be occur. So for the sake of the self commutation, we are only increasing the value of your alpha with the help of 165 degree. Okay, that is the highest limit. So by the changing of the value of the alpha, we can get a required speed control, or we can get the speed control for your required range by the means of the changing of your firing angle. Means if we are changing the speed control, or if you are changing the firing angle of your inverter circuit, okay, that is the in between 90 degree to 165 degree, so we are getting a different value of speed. So friends, basically transformer which is used in a circuit for the matching of the VD1 and VD2, because as we know that in the circuit we are using, okay, I can show you the circuit. So in circuit we are using one transformer. This will be the transformer. Why we are using the transformer? Because this will be using for the matching of the voltages of your VD1 and VD2. So by means of this transformer turns ratio, we can matching this voltage, and now this voltage will be supplied to your source. Okay, so that will be the concept. So friends, now we can understand what should be the relationship of that particular transformer's turns ratio. So for the sake of understanding, at we know that basically the transformer's equation, so we have the value of the VD1, as we know that this will be the VD1M, we call it as VD1M. So this is Vs max, so Vs max divided by N. So as we know that, why we are writing this equation, because as we know that at lowest speed required from the drive, VD1 will have the maximum value, and this VD1 will be having a maximum value. So we can rewrite this equation of VD1, that is Vs max divided by N, where S max we called it as, where the S max will be the slip at a lowest speed. Why we called it as the slip at lowest speed? Because as we know that when the value of your slip will be reduced, then obviously then your term of your speed control will be getting. So obviously in concern with that, as we know that the alpha value is restricted to 165 degree, alpha is restricted to 165 degree. So we are getting one important equation in concern with the V by M. So we call it as the equation, that is V by M cos alpha, this is cos 165 degree, is equal to or plus Vs max divided by N. Why we are taking 165 degree? So because we want to restrict the value of alpha is 165 degree, and from the fundamental equation of your converter circuit VD2, that is V by M into cos 165 degree, because 3 into root 6 by pi will be the constant term. So we are taking this term only. So friends, that particular term we are getting very important thing, because as we know that is cos 165 in a calculator we are getting the equation. I can rewrite, because most of the time in university examination such type of question will be asked to you. You have to prove that is m is equal to minus 0.966 n s max. So for the sake of that, I can again write the equation v by m into cos 165 degree plus v s max divided by n is equal to, now we can compute. Okay, so this will be the required solution. So as we know that cos 65 is, now we can rewrite that is v by m. So what should be the value of the cos 165? That will be the value, it is minus 0.966 plus vs max n. So we are getting the term, that is equation in concern with the transformers turns ratio, that is m is equal to minus 0.966 into n divided by s max, because in that particular equation this v and this v get cancelled, and we are getting the equation of your stator turn ratio to the transformers turns ratio with respect to the s max. So we are getting one important equation, because in concern with the university examination, one question is basically asked to you for 5 to 10 marks, that is prove that is m is equal to minus 0.966 n divided by s max, where n is called as the stator to rotor turn ratio, that is stator to rotor turn ratio, and basically m is called as a transformer turns ratio, or we call it as a source side converter transformer turns ratio, transformers turn ratio. Okay, so this will be the very important equation, because most of the time in university examination such type of question will be asked for 5 to 10 marks. Prove that is m is equal to minus 0.966 n divided by s max. So this will be the required derivation in concern with your slip power recovery scheme. So friends, in this way we have detailedly derived this equation. Now we want to understand what should be the relationship of your circuit, because as we know that for the understanding of your circuit we are getting one basic equivalent circuit of motor referred to the rotor, because as earlier we have derived the equation of your induction motor while we are referring with the help of the stator circuit, but now we want to understand the circuit with refer to rotor, because as we know that this will be the speed control method, which is called as this slip power recovery scheme. So in a slip power recovery scheme we are feedback the energy to your source side. So obviously in concern with that, now we want to understand the equivalent circuit of your induction motor referred to the rotor, because previously we are getting the word referred to the stator, but basically this will be the term which is called as referred to the rotor. So while we are referring, why we are referring this the rotor, because in this particular slip power recovery scheme we are feedbacking the best of energy in the rotor resistance to the source. So that's why we want to understand the circuit which is referred to the rotor. Okay, so friends, this will be the input voltage, that is S into V by N, that we had already discussed earlier. Okay, so this will be the sleep, this will be the voltage, this is a stator to rotor turns ratio, this is S R dash S. So it is called as basically the value, we call it as S is sleep. Basically the R dash S, it is the stator resistance. So it is stator resistance referred to rotor. So it is the stator resistance value which will be referred to the rotor circuit. Similarly, the second word, that is X dash S, because S is again slip. And what should be the value of the X dash S? So it is again stator reactance, but the stator reactance which is referred to rotor circuit. So that's why it is a dash. So it is stator reactance referred to the rotor circuit. Similarly friends, in this particular circuit we are getting XR. So what should be the value of the XR? It is the rotor reactance. We call it as the rotor reactance because previously we are getting this term differently, but in that particular slip power recovery scheme we are getting this term differently because these all terms are referred to the rotor circuit, and in previously it will be the referred to the stator circuit. And where RR, which is called as the rotor resistance, and as we know that this rotor resistance, stator resistance, and VR is the basically voltage across the source, that is VR, because as we know that we are injecting a power that is called as slip power into the rotor circuit. So what do you mean by VR? So we are getting the value of VR, that is voltage which is absorbed by power, that is VR. So this is the VR which will be the voltage absorbed by your rotor resistance. Okay, so this is called as VR. So this will be the equivalent circuit. So from that particular equivalent circuit we can getting one important equation, or we can getting very important understanding. So it shows that the DC link resistance, so the DC link resistance which is S into R dash S plus R dash R, because these two resistance, this resistance plus this resistance will give you, I can rewrite this equation. So this will be the S R dash S plus RR will give you the value, will give value, what it will give you value, that is 2 into S into R dash S plus RR. So this volt term now we can represent it by its a equivalent drive circuit. So this volt term we can getting by the means of the next circuit, which is we call it as a drive circuit. So it is equivalent circuit for the Scherbius drive. So in Scherbius drive friends we are using this VD1. So what should do you mean by that particular VD1? It is a voltage across the converter number 1. And what do you mean by VD2? It is the voltage across your inverter. So as we have this term, that is VD1, that is a converter voltage first, converter voltage second, and we can get this term, that is 2 times S into R dash S, where R dash S is called as the stator resistance referred to the rotor, RR is called as the rotor resistance, and RD is called as the resistance. I can rewrite this term. RD is called as the resistance of inductor circuit, the resistance of inductor, we call it as LD, that is a resistance of your inductor, that is LD. Okay, so this will be the called as the resistance that will be adding into the circuit. So this will be the equivalent value of your what, 2 into S into R dash S plus RR plus RD, because we are getting this volt term here friends. Okay, so now this will be the volt term because it will be addition of these two resistance, this resistance and this resistance. Okay, so we are getting this very important term of your equation. So this will be called as equivalent circuit. So friends, as we know that the RD is the resistance of a DC link inductor, so equivalent circuit ignores the commutation overlap of your diode bridge. So obviously this converter circuit now ignores the commutation of your diode, Now we can rewrite this equation because we want to find out the value of the ID from that particular circuit. So we are getting the value of the resistance or the current, that is ID is equal to VD1 plus VD2. As we know that according to the Ohm's law, if you want to get the value of the current, it will be voltage divided by resistance. So in that particular circuit, the resistance is basically available. So we are getting very important term because this should be the total resistance of your circuit. So ID is equal to VD1 plus VD2 divided by the resistance. So what should be the value of the resistance? 2 into S into R dash S plus RR plus RD. So this will be the value of your current, okay, which will be flowing through that particular equivalent drive. Okay, so friends, we are getting, or now we can substitute the value of the VD1 and VD2 in that particular equation. So we are getting the value of current, that is ID is equal to that is 3 by pi into root 6V. I can rewrite this term both combinedly. So we are getting term that is S divided by N plus cos alpha divided by M. okay, and divided by the volt term, that is resistance 2 into S into R dash S plus RR plus RD. So this will be the very important equation of what should be the value of the current which will be flowing through that particular drive circuit. Okay, so friends, now we can getting the value of the current, we are getting the value of the sleep. Now we want to find out the value of the torque of that particular equation. And so for the understanding of the torque of that particular equation, now we can rewrite, if we can, that is the rotor copper loss is neglected, so we can rotor copper loss will be neglected. So we are getting one important term, that is by considering or the neglecting the rotor copper losses. So as we have the fundamental formula, that is PR is equal to S into PG, I can rewrite what do you mean by the PR. It is PR is the power absorbed by, that is power absorbed by voltage source VR, voltage source VR, source VR. What do you mean by the PG? PG is called as the air gap power, air gap power, and S is called as the sleep, because in concern with that particular circuit we have find out the value of the sleep of your static Scherbius drive. So friends, we are getting one important term, because as we know that this is the PR is the product of basically this PR will be controlled by the changing of the firing angle of your circuit, that is the circuit which is called as a converter, that is VD2 into ID. So we can rewrite this equation, I can rewrite this equation number 1. So we can rewrite equation 1, we can rewrite equation 1, we can rewrite equation number 1. So the value of PR, now we can rewrite this equation of PR by means of this static Scherbius, that is VD2 into ID is equal to S into PG. So friends, from that particular equation we are getting the value of the PG. So we call it as the mod of VD2, because we are taking the magnitude of this term voltage VD2 divided by basically S. So this will be the value of your PG. So we can rewrite PG is equal to mod of, so we can rewrite again this term by changing term, that is PG is equal to mod of, that is VD2 into ID divided by S. So we are getting the value of the air gap power. So friends, if we are getting the value of the air gap power, so obviously we can getting, because as we know that in concern with your static Scherbius drive we are having one important concept that is called as mechanical power. As we know that mechanical power is equal to the product of, mechanical power is the product of basically torque and your speed. Now we call it as angular velocity, that is omega ms. So as we know that this mechanical power is developed by means of this basically PG, because in that particular circuit we are getting the air gap power. So that is PG is equal to, we are getting, that is T into omega ms. So if you want to get the value of T, we can rewrite, that is T is equal to PG divided by omega ms. So now we can substitute the value of PG. Now we can substitute, we can put value of PG into that equation. Now we can put the value of PG into that particular equation. Okay, so what should be the value of the PG that we had already derived here? We had already derived this value of PG here. So now we can substitute this value of PG into that particular equation. So we are getting the value of torque. So we can rewrite the value of your torque. It is torque is equal to, that is basically mod of VD2 into ID divided by S into omega ms, where omega ms is equal to 2 pi n by 60. Okay, so this will be the required solution of the torque of your static Scherbius drive. So this will be the very important equation in concern with your static Scherbius drive. So friends, in this way we have already derived the various parameter which is called as the sleep, that is sleep of your Scherbius drive. Then we have find out the current that is called as a current flowing through the driver circuit, that is ID, and we have find out the value of the torque in concern with your static Scherbius drive. Now we can understand what are the different advantages of your static Scherbius drive. So friends, as we know that this static Scherbius drive is very useful in the concern with the sleep power recovery scheme, because as we know that in static Scherbius drive we are getting the control of the value of the PR, and if the value of the PR will be basically from 0 to negative, positive, we are getting the speed control that is below synchronous speed and above synchronous speed. But in concern with the Scherbius drive, we are getting the speed control that is below synchronous speed because the value of the PR is positive. So friends, the first advantage of the static Scherbius drive, instead of the other speed control methods, working range can be obtained at any speed, because as we know that the value of the PR, if the value of the PR should be 0, then natural torque speed characteristics will be getting. The value of the PR will be positive, then the below synchronous speed will be possible speed control. So the range is very large. Below synchronous speed possible when PR is negative, then obviously above synchronous speed will be possible. So this will be the first advantage of your static Scherbius drive, because as concerned with the rotor resistance control, most of the power will be wasted. So in that particular static Scherbius drive, we are using the wastage of power that is feedback to the source. So that will be the first advantage. Then the second advantage of your static Scherbius drive is that if we are using over excitation control in the rotor circuit, so obviously it will lead the current. So if the leading current, so obviously the system performance will be more, because while we are injecting the voltage in concern with the that is source voltage, that is VR, into the rotor circuit, so obviously if we are injecting the voltage in that particular circuit, the current will be larger. If the current will be larger, according to the Ohm's law, current is directly proportional to voltage. So if we are increasing the value of the voltage, the current will be larging. If the current will be large, so obviously it will improves the system performance, because it will be obviously increasing the value of the current. So the performance of your system will be improves by means of the static Scherbius drive. Then along with that, certain disadvantages of your system, so that is called as the static Scherbius drive. So obviously in concern with that, the first disadvantage is that is sleep is inversely proportional to power factor. That is, we call it as sleep is inversely proportional to the power factor. So obviously if power factor will be decreased, then the value of the sleep will be increased, and if we are increasing the value of the power factor, the value of the sleep will be the decreasing. So this will be the one of the important disadvantage, because by the means of that particular static Scherbius drive, the power factor will be reduced because we are increasing the value of the sleep power. So if the value of the power factor will reduce, so this will be definitely affect your system voltage. So that will be the first disadvantage, because the static Scherbius drive will provide you the low power factor. Okay, so that will be the first disadvantage. The second disadvantage is that in that particular circuit we are using two converter. That is the converter number first, we call it as the VD1, we call it as the VD1 converter, and a second converter that is we are using the second converter, which is VD2. Okay, in VD2 we are using, this is the LD, the current flowing to that particular circuit RD. So this is the power, this is the power, that is three-phase power. So obviously in concern with that VD2 we are using some of the power electronic devices, and as we know that the converter angle of this VD2 will be limited to 165 degree. Why we are using this limited to 165 degree? Because due to the commutation problem. So this will be the one of the disadvantage of your static Scherbius drive. So instead of that various disadvantage, static Scherbius drive will be useful in a different applications. So the first application of the static Scherbius drive, it will be used for the narrow range pumps, because as we know that by means of that static Scherbius drive we are getting the speed control that is below synchronous speed. Below synchronous speed, I can take one example. Suppose if your rating of your motor should be run at the 15,000 rpm, that will be the use for your pump drive. Suppose if you want to get the speed control, okay, in between, that is below the synchronous speed or below the 1500, and if you want to get the value of the speed control, that is 400 rpm. So by means of that particular static Scherbius drive speed control technique, we can get the narrow speed range of your pump. So this will be the application of your static Scherbius drive. So as we seen that in that particular images, we are using a different types of narrow range pump, which is basically controlled by our static Scherbius drive. Similarly, The another application of your static Scherbius drive, it is used for medium and high power fan, because in industry we are using for the cooling purpose or the ventilation purpose, different types of fans are there, and for the controlling of this particular fan we can prefer the static Scherbius drive. So friends, in this way we have detailedly study about the first sleep power recovery scheme. We call it as the static Scherbius drive, because in static Scherbius drive we are controlling the value of your firing angle of your converter circuit number 2, and by means of the changing of the firing angle of that particular converter circuit number 2 we can control the sleep power, and now this sleep power is feedback to the source. So that's why it is called as the sleep power recovery scheme. So thank you.